Welcome back to Calculus 1. I'm Dr. Jeff Groh. Today we're going to talk about antiderivatives. To this point, we've dealt with limits and derivatives. Now we're going to work things backwards. We'll begin with a definition and a notation. We see that a function capital F of x is an antiderivative of the function little f of x if the derivative of big F is little f. Let's see how this works. Suppose that capital F of x is x squared plus 9. Note that its derivative is 2x. We say that x squared plus 9 is an antiderivative of 2x. However, there are other antiderivatives. You must be very careful from now on. Whenever you use a capital letter in representing a function, that implies that you're dealing with an antiderivative of the corresponding lowercase function. As another example, suppose that I have a function, little f, which is 3x squared. Can you give me an antiderivative? Clearly, one antiderivative would be x cubed, but wouldn't x cubed plus 25 also be an antiderivative? The answer is yes, because if I take the derivative of this f2, I still get 3x squared. As you can see, antiderivatives are not unique. However, there is a relationship between all of the antiderivatives of a given function. If big F and big G are antiderivatives of the function little f, then the difference between these two antiderivatives is equal to a constant. Antiderivatives differ by no more than a constant. Let's prove this. The way to prove it is to look at the following. We'll take the derivative of the difference between these two. We've assumed that both big F and big G are antiderivatives of little f, which means by definition they both have derivative equal to little f. And so the derivative of the difference is 0 for all x. Now, we proved that if a function has derivative equal to 0 on an interval, then that function is constant. And that's the end of the proof. We can make another definition. The indefinite integral of some function little f is denoted by has an elongated S-looking thing called the integral symbol, f of x dx. The integral symbol and the differential dx are matched pairs. They go together. If you start abusing the notation for dx, it will abuse you back. Be careful with this notation. It has an important purpose that we will explain later in the course. The indefinite integral represents the class of antiderivatives. A little f. In particular, if capital F is any antiderivative of little f, then the indefinite integral is going to be that antiderivative plus c, where c is an arbitrary constant. We know that all antiderivatives differ by no more than a constant for some given function, and so by adding an arbitrary constant c, we can describe the entire class of antiderivatives. I should also say that if you leave off the plus c on the exam, it's -1 point for each of those, and there will be a large number of those. So for example, the indefinite integral of 2x is x squared plus c. The indefinite integral of cosine x dx is sine x plus c. The derivative of sine is cosine. So an antiderivative of cosine is sine. The integral of 1 over 1 plus x squared is the inverse tangent of x plus c. Remember the one I asked you to remember. The derivative of arctan is 1 over 1 plus x squared. So the indefinite integral of 1 over 1 plus x squared is arctan of x plus c. We have a new version of the one that I want you to remember, and that is the indefinite integral of 1 over 1 plus x squared is the inverse tangent of x plus c. But of course, there is the other one that I want you to remember, and that is the indefinite integral of 1 over the square root of 1 minus x squared dx is the arcsine of x plus c. Don't forget the plus c's on these indefinite integrals. Now, recall we had the power rule for derivatives. If we took the derivative of x to the n, that gave us n x to the n minus 1. How does that work out for integrals? In this case, you have to have something with derivative equal to x to the n. And it really depends. There's two cases to consider. You do in fact get x to the n plus 1 divided by n plus 1 plus c if n is not -1. If n is -1, x to the -1 is 1 over x. And we know that's the derivative of natural log. And so you'll get the natural log of the absolute value of x plus c if n equals -1. Notice that if we take the derivative here, the n plus 1 comes down and cancels the denominator, and we subtract 1 from the exponent. That leaves us with x to the n. Down here, the derivative of natural log of absolute value of x is 1 over x. Don't forget the absolute values. I'll mark you off 1 point if you do. Just for special emphasis, let's write this down as a rule. The power rule for antiderivatives. It goes like this. First of all, if it's 1 over x, that's your n equals -1 case. You get log absolute value of x plus c, but otherwise, you get x to the n plus 1 divided by n plus 1 plus c when n is not -1. Don't forget, for antiderivatives, you add 1 to the exponent and divide by the new exponent. As an example, if I'm integrating x to the 4th, I'll have x to the 5 over 5 plus c. Note that the derivative of x to the 5th divided by 5 plus c is x to the 4th. We need a theorem telling us some of the properties of the indefinite integral. First, if you integrate a constant times some function, you'll get the same thing if you take that constant times the integral. Second, if you integrate the sum of two functions, you'll get the same thing if you integrate separately. When you combine the arbitrary constants from the two integrals, the sum of two arbitrary constants is an arbitrary constant. I should mention that these are pretty easy to prove. Suppose I'm integrating, say, 3x to the 4th plus 5x minus 7. Because of this last theorem, we can break this into 3 integrals and integrate term by term. And on the first term, we can move the 3 out and just integrate the x to the 4th by itself. In integrating 5x, the 5 comes out, and we'll have 5x squared over 2. Integrating 7 just gives us 7x, and then we can add an arbitrary constant of integration. What do we get if we integrate secant squared x? We need to find an antiderivative of secant squared. What function has derivative equal to secant squared? The answer is 10x plus c. The derivative of tangent is secant squared. So the integral of secant squared is tangent plus c. What do we get if we integrate the square root of x? First, write it as a rational exponent, and then use the power rule. You have to add 1 to the exponent. 1 plus a half is 3 halves. But we have to divide by that new exponent, 3 halves, which means we'll multiply by the reciprocal, 2/3, plus an arbitrary constant c. In our next example, we'll integrate 3 cosine x plus sine squared x over sine squared x dx. We need to break this into 2 fractions. On the first part, it's going to be cosine over sine, which is cotangent x, and a 1 over sine, which is cosecant x. On the second term, we'll just have 1. We can integrate the two terms separately. On the first term, we have to think about what function has derivative equal to cotan x cosecant x. The answer is negative cosecant x. And what function has derivative equal to 1? Well, x, of course, plus an arbitrary constant c. One can check this answer by direct differentiation. How do we integrate x squared plus 1 times 3x minus 5? The answer is, you have to FOIL this out first. You'll have 3x cubed minus 5x squared plus 3x minus 5. And then we just integrate term by term. 3x to the fourth over 4 minus 5x cubed over 3 plus 3x squared over 2 minus 5x plus c. Suppose I'm integrating x to the 7th minus 3x to the 5th divided by x cubed. The way to approach this is to divide x cubed into each of the terms in the numerator. Remember to subtract exponents. We'll have x to the 4th minus 3x squared. The antiderivative then is x to the 5th over 5 minus x cubed, and then plus c. You might be surprised to learn that there is no product rule or quotient rule for antiderivatives or for indefinite integrals. In fact, there's a whole chapter in Calculus 2 devoted just to techniques of finding antiderivatives. For another example, suppose I'm finding the indefinite integral of e to the x dx. What function has derivative equal to e to the x? Well, this ought to be easy. E to the x plus c, of course. Suppose I'm integrating 1 over the square root of 1 minus x squared plus 1 over x. The first term is the other one. The other one you're supposed to remember. And the second term gives us log absolute value of x plus c. Don't be forgetting that absolute value. Many physical laws are expressed in terms of how things change, i.e., the derivatives of various physical quantities. In our next example, suppose f prime of x is 2x and f of 0 is 3. Find f of x. This, by the way, is called an initial value problem. Whenever I have the derivative of a function given and the value of the function at one point, that's called an initial value problem. The goal is to undo the derivative, which we can do using the indefinite integral. F of x should be the integral of the derivative. Which we now know to be x squared plus a constant. The point of this initial condition is to tell us that when x is equal to 0, y is 3. And that tells us what the constant of integration is. Putting this together with this representation of f here, we deduce that f of x is x squared plus 3. Initial value problems give you what is called a differential equation. an equation involving the derivative of some function that's not explicitly given. They also have some piece of data, some point that the graph goes through. That's necessary because when you undo the derivative using an indefinite integral, you have an arbitrary constant of integration. That gives you a one-parameter family of curves. But after doing this integral, we end up with a family of curves. Specifying when x equals 0, y equals 3 says we want the solution curve that passes through a particular point. And there should be one and only one of those. And that gives us the function we see. Let me give you an example that might hit home. Galileo performed experiments that showed that objects do not have an inherent velocity, but rather a constant acceleration. Acceleration is the time rate of change of velocity. And Galileo showed that this is some constant, which I'll denote by minus g. This gives me a differential equation. I can turn this into an initial value problem if I assume that the velocity at time 0 is some constant v0. Our function v should be the integral of dv dt with respect to t. That's the integral of minus g, but g is constant. So we get minus gt plus a constant of integration according to our definition for the indefinite integral. Now we take advantage of this initial condition. v0 is what you get when you plug in t equals 0. So the constant of integration is in fact the initial velocity. That tells us the velocity as a function of time is the initial velocity minus the acceleration due to gravity times time. You might remember this formula from your courses in physics. We can go further. If v of t is v0 minus gt, remember that velocity is the derivative of the position function. So the derivative of the position function is going to be the constant initial velocity v0 minus the acceleration constant g times t. To figure out s, we need to undo a derivative. We need to integrate. Keeping in mind that v0 is a constant. Its integral is v0 times t. Here, we're integrating with respect to t, where g is a constant. Using the power rule for antiderivatives, the integral of t is t squared over 2. And we must add a constant of integration. If the initial position at time 0 is some initial height, h0, what does that tell us about the constant of integration c? h0 will be the height at that time, time 0. When we plug in 0 for t, we end up with v0 times 0 minus g times 0 squared over 2 plus c. The constant of integration is the initial height. It follows then that the height as a function of time is the initial height plus the initial velocity times time minus 1/2 g t squared. You might remember this from your courses in physics. Let's think back about how we derived this formula. This formula came from the simple observation that acceleration is a constant, minus g. Acceleration is the derivative of velocity. To find the velocity, you undo that derivative by integrating. When we do, we get an arbitrary constant of integration. Using an initial condition, we determined the constant of integration to be v0. Integrating again, we found the position function. Using another initial condition, we determined the second constant of integration to be the initial height. That gave us this formula. The formula we just derived is interesting because it overthrew millennia of misunderstandings about the nature of motion. Aristotle had taught that objects had an inherent velocity that they achieve instantly upon being released. Galileo, through hard experiment, proved that that was untrue. We should do a few more examples. Suppose I'm integrating 1 over x cubed. You cannot apply the power rule directly until you move the x cubed into the numerator. Once you've expressed the integrand in this form, the integrand is the thing you're integrating, you may apply the power rule. Adding 1 to -3, we get -2. We divide by that new exponent. Simplifying, our answer is -1 over 2x squared plus c. Let's suppose we integrate sine x. We get negative cosine x plus c. Remember, the derivative of cosine is negative sine. So if I were to take the derivative of negative cosine x, I would have positive sine. Let's integrate x plus 1 over the square root of x. First, you have to think of x as being x to the power 1. We'll rewrite this by breaking this into two fractions. On the first one, remember to subtract exponents, where the square root of x is x to the 1/2. We'll end up with x to the 1/2 plus x to the minus 1/2. Now we may apply the power rule for antiderivatives to both terms. We'll have x to the 3/2 times 2/3 plus x to the positive 1/2 times 2 plus c. What do I get if I integrate just dx? This may seem like a trick question, but it's not. What we're really integrating is the function 1. So we need to know what function has a derivative equal to 1. The answer is, of course, x plus c.